Okay, so we're going to be looking at this concept of moments, and this is all about measuring or understanding the effect of objects which are rotating. And this effect only really comes, or is only really noticeable when you start modeling objects in mechanics as actual physical objects with a size and a dimension, as opposed to single points or particles, which is something that we do quite often in mechanics. Is we just say, oh, it's a particle, or model this, this object as a single point. So just to get us into sort of the theme of the topic, I'd like you to see if you can think of a way to answer the following. So what forces and mechanical effects might you need to consider when modeling objects as a large body as opposed to just a single point or particle? So for instance, gravity clearly affects both, right? It doesn't matter if I model, if I say, for instance, my coffee mug sitting on the table, if I model it as a mug shape, maybe a rectangle with something appended on the side, or as a single dot, it doesn't matter, gravity will still affect it in the same way within the model. But there are things which will only need to be taken into consideration when it's an actual object rather than a dot. So see if you can think of at least three. I think I've got four in mind, but there could be more. If we were doing this live, perhaps you could think of loads, but see what you come up with. How does it differ? What other effects are there? Okay, hopefully some of you will have tried to think of a few. So one example is air resistance. Okay, so air resistance is sort of the eternal, assumption within mechanics. So if I model something as a single point, then it almost effectively has no surface area. So if it falls through the sky and I'm modeling it as a dot, the air is having no effect. Whereas in reality, if I drop something which has physical space and dimension, it has a surface area. The air is almost, well, is quite literally the air particles are whacking against this object as it falls or as it moves through physical space. So air resistance only affects things if you consider them to have a physical dimension, right, rather than a dot. So one is air resistance. Another, I found it difficult to how to phrase this, so perhaps you came up with something like this: physical space or collisions. So I think collisions is probably the better way to put it, actually. If I model two objects as dots, then in reality they can never really hit each other, right? Because no matter how close they get to each other, they can always get closer, right? There's an infinitely divisible amount of space between any two infinitesimal points. But in the reality of the universe we live in, objects aren't just infinitesimal points. They have a width, they have a height, they have a depth. It means they can hit each other. So you've got collisions going on. So that's another thing that you might want to consider. A third thing I could think of is friction. So again, if I model something as a dot, it has no surface area, and therefore there can be no friction, right? Because friction is only caused, or it's a phenomenon that only exists because two objects touch each other and have a surface in common, effectively. It's also why the larger the surface area of contact, the more friction you'll experience. So a single point doesn't experience friction, not in the models. So points generally are quite bad for modeling a lot of phenomena. And then the fourth is what we're actually going to talk about today, which is rotational forces. Okay, if I model something as a single dot, then the concept of rotation doesn't make any sense. What does it mean to rotate something that has zero dimension? Whereas if I have something that has physical dimension, or 2D or 3D or even 1D, then it can rotate, right? It can tip over. Hopefully not this particular mug, but a dot cannot. So that's what we're going to look at today. These forces, these moments of forces, are going to describe how things tip over, how they rotate, and so on. So let's take a look. So the first thing we need to do is just define this term. I'm going to be talking about a few sort of bits and bobs. So this is your sort of primary note-taking opportunity, and where we're mainly just going to explain what these things are. So a moment is effectively a physical or mathematical concept. It's actually a generic term. So if you go on Wikipedia or Google and you look up what is a moment, it might come up with what we're talking about today, but it might also come up with other things. So there's many kinds of moments. A moment is effectively just a special value. But in this case, we're talking about something called moments of force. So the full name, I suppose, of what we're studying today is moments of force, or a moment of a force. You might, and this is especially the case if you're looking for the wiki page on this, want to look up this word torque, which is, I suppose, the more proper scientific name for this. In A-level or at school, we talk about moments of a force, but I think at higher levels, and probably physicists will refer to these things as torque, or engineers, they'll talk about torque. So it's some quantity which we have defined, and it's useful to define it, and we'll see why it's useful later. But first we just want to define it. So given any force, we can define a torque or a moment. I'll be calling it moments from now on. We can define a moment of a force, and all we need to know is two things. And they are as follows. The moment of a force depends on, number one, the magnitude, so the size of the force or the length of the force vector, and number two, perpendicular distance, and number two is the trickier one, so we'll have a bit of practice of that. Perpendicular distance from a reference point. Okay. And what is this reference point? So actually, the moment of a force is not an absolute thing. So you can't just say to someone, you know, I've got a force of 10 newtons, it's going in this direction. What is the moment of it? That doesn't make sense unless you first define a point, a single point in space, 2D or 3D, which is your reference point. To give you an analogy, it's a bit like saying, what's the potential energy of an object? Or perhaps that's not quite applicable to people who haven't done further mechanics. Okay, let's keep it simple. It's a bit like saying, how high up is this object? How high up is it? It depends. Are you taking the ground as zero? Usually yes. Or are you taking sea level as zero? It depends where your 0 point is. Right, so how high up something is depends on what you call zero. If you take it as sea level, it will be one number. If you take it as the earth, you know, solid ground, it might be another number. If you take it as, you know, height from the top of the roof, it'll be a different number. So in the same way, the moment of a force is not some fixed thing. It depends on your reference point. So you need to choose a reference point first, and then you can define the moment of a force. So let's actually give you the formula for it now. Okay, so the moment of a force equals, so we said what it depends on, but we didn't say how it depends on them. It's actually the product of these two, right? It's the product of its magnitude and perpendicular distance. So let's write it as follows. Moment of a force F equals, let's just write mod of F to mean magnitude, times D, and then I'm just going to say D is defined as perpendicular distance. And then what we're going to say, instead of saying reference point, let's just say from point P. And then let's be a bit more specific when I say moment of a force F. The full way of expressing this is the moment of a force F about the point P. Okay. And we use the word about here just to talk about the idea that it's ultimately going to be a rotation going around something or going about something. So this is the formal definition, and it's the thing that we need to make sure we're going to understand today. The moment of a force F about a point P is the magnitude of F times the perpendicular distance of that force from the point P. Okay. And there's one last thing I just want to mention, which is what are the units of this thing, right? So distance meters, mass is kilograms. Moments also have their own units, and quite easy to see what they are if you just consider the formula, right? So newtons, oh, I've revealed it there. Force, magnitude, is measured in newtons, and this D is going to be meters because it's a distance. So moments have the unit of Newton meters. Okay, it's N, big N, little m, right? Newton meters. That's the unit of moments. Okay, and we're going to be calculating moments for various forces, and we'll see how we can use that and make it useful. Just before we do that, though, I think I want to talk a bit more about this perpendicular distance from a reference point, because I think it can confuse quite a few people. So let's take a look at that. So the way I'm going to do this is I'm going to make a point, my reference point, let's call it P, and I'm going to draw a bunch of vectors now. Let's see, let's do that one, let's call it A. Let's mix it up a bit actually. Let's do, let's say this one, B. Let's see, maybe this one, C. Let's do this one, D. Okay, what I'd like you to do is as follows. A, B, C, D, each of those forces roughly the same magnitude, but their perpendicular distance from P is different. And let's see if you can do this correctly. Can you put them in order of shortest to longest perpendicular distance from that point P? Okay, so I want you to take those four letters A, B, C, D, put them in order from shortest to longest perpendicular distance. Please do that, and then I'll give you the answer, but try and do it yourself first. Pause the video now, see what you think. Okay, so let's have a visualization on this. So A, or let's do the easiest one. I think the easiest one is C, and I'll tell you why I think it's easiest. It's because if I take the perpendicular line from C that goes through that point P, I'm tilting my head slightly. Okay, so this is an attempt at a straight line. Okay, this is my D, right? Let's call it the CD because it's the D that belongs to the vector C. Okay, so it's quite long. That's the perpendicular distance. Very importantly, this is a right angle. Okay. Then what about something like, say, A? Similarly, it just misses. Right, I'm actually going to extend A slightly and then find the perpendicular distance. Okay, and we've got it there. Okay, so that's our AD. Okay, now this thing I just did here, this wasn't me just trying to correct a bad drawing. You can't always connect the perpendicular distance to the vector itself, and you may need to extend it a little bit, at least graphically, when you're trying to visualize it. And I think that becomes very apparent when you look at B. Right? The perpendicular distance of B from P is the following. You need to extend, at least visually, you need to extend that line of the vector. Oh, that's really bad. I don't have a... It's quite difficult to draw a straight line here, but I'll give it a go. Okay, there we go. You extend the vector, and then you're going to draw in that perpendicular distance so that it makes a right angle. Okay, because otherwise I wouldn't get a right angle. So this very short distance here, that's the actual perpendicular distance BD. Okay, so quite often you will have to do that kind of extension. Sometimes you won't, but be aware of it. For D, we do have to do it, right? We're going to have to extend D, right? So technically we extend in either direction. It's effectively an infinite line, right? Each of these vectors is kind of defining an infinite line. And then from that infinite line, we're going to draw a perpendicular line that passes through P, but meets at a right angle to that infinite extension. Let's call it the infinite extension. That's not a technical name, that's my name. But this infinite extension of a vector needs to meet the perpendicular distance at this right angle. And there we have it. That is our, well, our DD, I suppose we could call it. So final answer, I would say in order, B first, and then I would say probably D second, A third, and C fourth. I would go for B, D, A, C. Looks about right. Perhaps you might have D and A in a different order, but yeah. Okay, so that's the key thing. Is I think that's the one thing people get wrong quite a bit. What you're definitely not doing. Let me just give an example of what not to do. You're not going to take a point P and then a vector, like say this one, and just draw some line that goes from P to the vector, right? That's wrong. That's not the perpendicular distance. It has to be perpendicular, which means you have to extend that vector infinitely and then draw the actual perpendicular distance there. Okay, cool. So I think we've defined our terms clearly now, right? We know magnitude of a vector, we know what that is anyway, and now we've defined perpendicular distance. So now we should be able to calculate moments of vectors. So just before we jump into an example, there's one more little caveat, something which I haven't mentioned yet about moments. And that is that they can either be positive or they can be negative. Now, so far, I've said a moment is the magnitude of force times the distance, right? Now, the magnitude of a force is always positive, and the distance is always positive. So you might think, why would a moment ever be negative? And that's because you need to tweak slightly the formula that I gave earlier to effectively say that that's the magnitude of the moment, right? So it'll give you the moment, but then you still need to either make it plus or minus, and how you choose whether it's plus or minus all depends on the following. It depends on which direction, clockwise or anti-clockwise, you are considering to be positive. Because we're talking about rotation. Moments are all about rotation. So if I, let's throw an example. If I have a point here and this force, to you, does that look like a clockwise or an anti-clockwise situation? So the way to visualize it is as follows. This point is kind of, well, it's a point which this force here is trying to go around, right? It's trying to rotate around that point. So it's almost like you're imagining a circle. It doesn't matter how big or small it is. That arrow is trying to go in a circle around the point. So which way is that circle going? It's going anti-clockwise, right? That's anti-clockwise. Let's try another one. If I do that, then the force is going around the point like this. Okay, so that's clockwise, right? So we have this subtle concept here where if I draw a vector and a point, I instantly create this concept of either a clockwise or an anti-clockwise direction, right? That one's clockwise. Let's see if I can do another anti-clockwise one, like this. There we go, it goes that way. That's anti-clockwise. Okay, so one of them is positive and one of them is negative. It doesn't actually matter which one is which. I think the textbook says clockwise you take as positive, but really all that matters is that within a single question or problem that you're working on, you must assign one of them as positive and one of them as negative. It's a bit like, let me just put the default here actually. Let's say call this default, clockwise is positive, anti-clockwise is negative. It's a bit like when you're making a force diagram, you can either say moving right is positive or moving left is positive. Or you can say moving up is positive and moving down is negative. Did I say positive twice in the previous example? Sorry if I did, can't remember. One direction is positive, the other is negative. Which one it is doesn't matter. So you choose. It's similar to that with moments. Choose which one you want to be positive. If you're indecisive and you don't want to make decisions, then just go with that as your default. Clockwise positive, anti-clockwise negative. Okay, so let's look at an example. We're going to find the moment of each force about the point P in each of these examples. They're two separate examples. So let's look at A. The force, the magnitude of the force in this one is 6. And what is our perpendicular distance to P? It's drawn on there perfectly for us, right? A right angle here, very important. So the distance is 3. And therefore we get FD equals 18. So now if you're thinking, okay, well, by the way, Newton meters, do I put a minus or not? Because you said I could choose. Well, what you should do is, if you're not actually going to be using it in a calculation, you're just stating the moment, like it is here. What you should do is just use the word clockwise or anti-clockwise. It avoids all ambiguity, right? It's a bit like if I say, you know, this object moved minus 5 meters. Does that tell you it moved left or right? I have no idea. You didn't tell me which way was positive. So instead of saying minus 5, I might just say it moved 5 meters to the right, or it moved 5 meters to the left. So that analogy applies here. Instead of saying minus or plus, we'll just go with the plus version, but then we'll say, in this case, anti-clockwise. So we'll write the word anti-clockwise, and this is how the exam and the textbook also recommend doing it. We can see it's anti-clockwise because I can draw a circle where that force goes around the point P. Okay, and then let's do part B up here. Right, so P, remember we've got this random sort of line, and then this line here is the actual vector, the actual force. So the force magnitude is 12 again, well not again, but the force magnitude is 12. The perpendicular distance D is this thing, not the 8. So we need to do a bit of extra work, and this is what will be common. You're going to have to use trigonometry to figure out the actual perpendicular distance. So in this case, it's the opposite of that triangle, and because it's perpendicular distance, it will be a right angle triangle, which is convenient. So that's going to be 8 times sine 35, because it's the opposite. So then our moment is going to be 96 times sine 35, and that equals 55.1 Newton meters. And which direction is it going? About the point P, it's going in a circle like that, in that direction, if I follow the arrowhead of the vector. So that's clockwise. Okay, and we've done it. So that's a moment. That's how we define it. We're actually going to use them properly next session, I think. At the moment, that was not intended, but at the moment, what we're effectively doing here is just working with a definition. It hasn't been made clear what the point of any of this is. So if you feel like at the moment this seems pointless, it's because the point hasn't been given to you yet. We need to just define our terms first. So I think next is questions. Let's take a look. I know I've got one more example, and then I'll give you some questions to do. So we've got a diagram showing two forces, this 5 newtons and this 8 newtons, acting on a laminar. Find the moment of each of the forces about the point P. just to note, in case you don't know what this means, it doesn't really matter for this question. A laminar is basically a flat 2D thing. So a laminar, if you think, for example, laminating, when you laminate a piece of paper is an example of a laminar, right? A mouse mat is like a laminar. A paper plate, if it's properly flat, is a laminar. Or if I cut any sort of funny shape out of it. So laminar, just think of it as a 2D object, right? A thin 2D object. By definition, it will be thin because it's 2D. So what we're seeing effectively in this image is kind of like, imagine, you know, this is all happening on a piece of paper, right? So there's a point on this piece of paper, this laminar, and around that point you've got these various forces, these two forces. So it's almost like if you imagine I had a piece of paper and I was pushing on it at some place in one direction, I could make the paper rotate, right? And if I've got two fingers in two different places pushing on it, who knows what's going to happen. All sorts of exciting things have happened with that paper. So the moments are going to tell me what happens. Again, for next session we'll talk about how we can figure out what will actually happen. But let's figure out the values of these moments first. So it doesn't actually have a part A and B, but we need to be explicit here. So we're going to say the moment of the 8 Newton force about P. Let's do that one first. In this case, we've chosen the harder one to do first. That's fine. So in this case, that 2 meters, that's not the perpendicular distance. So we're going to have to do some geometry and just diagrammatically draw it on. Okay, so that purple line is what I actually want. So that length of purple is going to be 2 times, in this case, that angle tells me it's the opposite, so 2 sine of 50. So then going back to here, I've got the magnitude of the force is 8 times its perpendicular distance, 2 sine 50 is 16 sine 50. I put that in the calculator, and what do we get? Should be 12.3 Newton meters. And it's going, in this case, anti-clockwise. Okay. And then our first, or perhaps second, force is a moment of 5 newtons about P, and this one's much easier. It's going to be 2 times 5 is 10 Newton meters, and again we want to know the direction. It's going clockwise, this one. Okay, so you might not, we haven't really talked about it properly yet, but already I think hopefully we're getting some idea that these forces are kind of providing a rotational element to movement, right? So forces don't just push and pull, they also rotate. And the fact that one of them has a moment of 12.3 and the other one has a moment of 10, hopefully we can, with a bit of intuition, see that we're going in the direction of one of these is overcoming the other. The 12.3 Newton meters is a bigger moment than the 10, so probably that force is going to win in some sense. If you've got one thing pushing you clockwise, another thing pushing you anti-clockwise, one of them's going to win. You're only going to end up going in one of those two directions. Okay, cool. All right, so for the rest of the time, I'll give you some questions. We're just going to calculate moments of various forces, make sure we're doing it correctly. So I've got 2 slides, 5 questions total, 2 on this one, 3 on the next. This slide, I think, won't take you too much time at all, just a bit of trig, and just make sure you write your answers out fully. State each time if it's going clockwise or anti-clockwise. State the units, write down Newton meters. Check your work in the back of the textbook, see if you can get all 8 of these correct first time. Good luck. Pause the video now. And then have a go at these. So here it's less, the diagram is given to you, I guess not in a more obscure way, you're more given a realistic scenario rather than just a force and a point. In particular for 4, think carefully about this, because now we're getting into sort of the real world. You've got forces acting on a laminar, I suppose, and you want to be careful about this perpendicular distance. It can sometimes be 0. So keep that in mind. Perpendicular distance can sometimes be 0. You can sometimes have a moment equal to 0. So have a go at these 3, and then you're done. Pause the video now.